Hi. Sometimes the dimensional tolerances are not enough to ensure the function of a part in a mechanism.
We can see in this image that the dimensions are not enough to ensure the fit. So we add some information that complements dimensions. It is known as GD&T, geometric dimensioning and tolerancing. Let's see an example of why geometric tolerances are so important. We design a table and the height has a tolerance. Assume all table legs are cut at the same time. As the table height is dimensioned, the following table would pass inspection. It's not flat, but inclined. Despite that, the table would pass. You can solve that by using GD&T. The table may be any height between 26 and 28 units. The table top must be flat within 1/16 units. Let's see now the parts of the geometric tolerance indication. The main part is the feature control frame, which is divided into compartments. The first one contains the type of geometric characteristic, such as true position, profile, orientation, so on. The second compartment contains the tolerance. The remaining compartments contain the datum planes or axes in the proper sequence. There are different types of characteristics and we'll go in depth later. Before that, we look at the other part of the indication, which is the arrow. If the arrow is pointing at the surface, it indicates that that surface is the reference one. If the arrow is an extension of the dimension line, it will indicate the axis or symmetry plane. Finally, if the arrow of the frame is indicating or pointing at the axis, it means that the tolerance for all the elements is related to that axis. Now, let's go into detail about the characteristics. First, we have the straightness characteristic. The straightness of the feature, in this case the generatrix of this cylinder, must be within 0.05 mm tolerance zone. In this example, we can see how in the first case the arrow is pointing at the axis, so both parts are affected by the tolerance. In the second case, we can see the arrow is pointing at the extension of the dimension line, which means that the tolerance only affects to the left side part. This is the flatness characteristic. In this case, the tolerance zone is a zone held between two parallel planes a certain distance apart. In this example, all points must be between two planes 2 microns apart. In this example, every point on the top surface must be within two parallel planes a distance 80 microns apart. The circularity characteristic indicates that the real curve must be between two circumferences whose radii difference is the tolerance, in this case 80 microns. The cylindricity characteristic is a combination of circularity and straightness characteristics. The real cylinder must be between two cylinders whose radii difference is the tolerance. The parallelism characteristic is quite similar to the flatness one, but in this case we need a reference plane. It's indicated by the datum. The tolerance zone is a zone held between two parallel planes parallel to the datum plane, and a distance 30 microns apart from each other. Here we can see another example related to an axis. We also can see the inspection methods for these tolerances. In this example, taking as a reference the right axis, we can see how the left axis must be within a cylinder with 30 microns diameter. Another characteristic of orientation is perpendicularity. The tolerance zone is a zone within a cylinder of certain diameter, in this case 10 microns, perpendicular to the datum plane, in this case the B plane. In this example, we can see how the right plane must be between two parallel planes. Both are perpendicular to the datum plane, which is the bottom one, and spaced 5 microns apart. Angularity characteristic is very similar to the perpendicularity, but in this case we are not restricted to 90 degrees, but we have to indicate the angle between the reference plane, the datum plane, and the surface we are indicating the tolerance. Positional tolerances are probably used more than any other geometric control. It is used to locate features of size from datum planes such as a hole or keyway, and used to locate features coaxial to a datum axis. The concept is there is an exact or true position that the feature would be if it was made perfect. However, since nothing is made perfect, a tolerance zone allows deviations from perfection. The exact location of a feature of size is defined by basic dimensions, which is shown in a box, as you can see in the image, and are established from datum planes or axes. In this example, we can see how the 4 holes of diameter 30 mm must be within a cylinder of diameter 0.2 mm. The coaxiality characteristic defines a tolerance zone which is the one within a cylinder of certain diameter whose axis agrees with the datum axial straight line, as you can see in the image. The symmetry location characteristic defines a tolerance zone which is held between two parallel planes, a distance, in this case of 25 microns apart from each other, and arranged symmetrically to the datum median plane. Run-out tolerances control the relationship of a feature relative to a datum axis established from one diameter or two diameters separated axially. Secular run-out controls the cumulative variation of secularity and coaxiality for features constructed around a datum axis and secular elements of a surface constructed an angle not parallel to the datum axis. Total run-out controls the entire surface simultaneously, hence it controls cumulative variations in circularity, coaxiality, straightness, taper, angularity, and profile of a surface. This has been enough for today. See you in the next lesson.